This video is going to look at calculating the center of mass in different situations. The first situation will be looking at the center of mass for individual objects. The next situation will get into things where you have continuous mass distributions, where you have extended objects and we're trying to calculate the center of mass of those. So in this first situation, we have three objects that are lying along the x-axis. To calculate the center of mass for individual objects, the equation is that the x-coordinate of its center of mass is m1 times its position x1 plus m2 times its position x2 plus m3 x3 plus m4 x4. You take each mass and multiply by its position, and then in the denominator you divide by the total mass. You add all of the masses together. So we're going to look at this first situation where we have these three people standing on the sidewalk. We're told to let x equals 0 be where the 70 kilogram person is standing. This leftmost person is at x equals 0. So the first step is we need to label their positions. So the first person is at x equals 0, the second person is at x equals 2 meters, and the third person is 4 meters to the right of that person, where he's at x equals 6 meters. And we're just going to use the equation given to calculate the center of mass. It's going to be m1 x1 plus m2 x2 plus m3 x3 divided by the total mass. So putting in those values, we have 70 kilograms times 0 meters plus 60 kilograms times its position 2 meters plus 82 kilograms times its position of 6 meters divided by the total mass, 70 kilograms plus 60 kilograms plus 82 kilograms. That gives us 612 kilogram meters in the numerator and 212 kilograms in the denominator, which gives the center of mass of 2.8868 meters. That position of the center of mass is a little bit to the right of that middle person. So calculating the center of mass for individual objects is fairly straightforward, and you can do this for the x and y directions. If you have something on the x and y axis, you would do this for the x coordinate of the center of mass, and separately you would do it for the y coordinate of the center of mass. If we don't have individual point masses and we have mass spread out over 1 or 2 or 3 dimensions, we have to talk about mass densities. The typical type of density that you talk about first usually is this volume density. Density is mass per volume. So if we have a three-dimensional object, if we take the total mass divided by the total volume, that gives us the volume density of the object. But we can also talk about something where the mass is spread out just in 2 dimensions. Think about just a piece of cardboard. If we look at the mass of the piece of cardboard and the surface area of the piece of cardboard, we can talk about the surface area density. Or if we have the mass spread out in 1 dimension, so something like a thin rod, we can talk about the mass per length of the rod. And the way that you do this is you break the object up into individual pieces and you add up each of those pieces, just like we did for the individual objects. So we're first going to look at this one-dimensional case, and what you would do is you would break this rod up into individual pieces. This little tiny piece has a width dx. It's a little tiny piece dx. The mass of that little tiny piece is the linear mass density, the mass per length, times the length of that segment dx. So again, for a linear object, we don't have mass per volume, we have mass per length. And if it's a uniform density, you just take the total mass divided by the total length. So we're going to look at this case where we have a rod with a total mass m and a length l that has a uniform density. And we're going to find the center of mass of this rod. Now this might be something that you already know. If you have a meter stick and the meter stick is uniform, the center of mass is going to be right at the center of the meter stick. And so what we're going to do is we're going to show where that comes from. So we take this rod, we break it up into these little tiny pieces. This arbitrary piece here, it's a distance x from the left end of the rod. It has a width dx. The little tiny mass of that piece, dm. Again, we're using dm to stand for the infinitesimally small mass of that infinitesimally tiny piece. So the mass of that little tiny piece dm equals the total mass m divided by the total length L. That's the mass per length. This m over L is lambda, that linear mass density. So it's the mass per length times the width of this segment, dx. And so to find the center of mass of an extended object, the equation becomes 1 over the total mass times the integral of x dm. Again, this is the same equation that we had before, the m1 x1 plus m2 x2 plus m3 x3, and so on and so on and so on, all divided by the total mass. So we have each little piece dm times its position x. This integral is the sum over all of those infinite number of pieces, and then we're dividing by the total mass. Looking at this integral though, x is our variable, but it says that we're going to integrate with respect to m. We need to be able to write dm in terms of x. And that's what we did up here. dm is the mass per length times dx. So we can use that substitution. We can substitute that in, and then we have an integral that's just in terms of x. So we substituted in the dm was m over L times dx, and then we're going to integrate along that rod. We're going to integrate from x equals 0, when we're at the left end of this rod, all the way out to x equals L, which is the right end of the rod. And so this m over L is a constant, so it can get brought outside the integral. So we have m divided by m times L, and it's the integral of x dx. And so those masses cancel. So out in front of the integral, we have 1 over L. The integral of x dx is x squared over 2. So we have 1 over L times x squared over 2 evaluated from 0 to L. And so evaluating that, we plug in our upper limit L. So we have L squared over 2 minus our lower limit 0 squared over 2. So we have 1 over L times L squared over 2. That's L squared over 2L. The L divides out, and we're left with L over 2, which again, that's what we said. If we have a meter stick with a uniform mass distribution, the center of mass is going to be right at the center of the meter stick at the 50 centimeter mark. If we have a uniform object with a uniform shape, then the center of mass is going to be right at the center of that object. That's a property that we can use. If you have something, if the meter stick was thicker on one end than it was on the other end, then we have more than one dimension there. We have to get into that, and we'll learn how to take that into account in another example. But here, if we have a nice symmetric meter stick and it's a uniform density, then the center of mass of that meter stick ends up being right at the center of the rod.